Hey everybody, I hope you guys are doing well today. Um, for today's class meeting, we are going to be talking about practical sources, and then a little bit later on, once we get a handle on practical sources, we're going to talk about the maximum power transfer theorem. I want to preface this lecture by saying that this is one of the topics that I enjoy teaching the absolute least. In fact, it's one that I'm campaigning to actually get removed from the class. It's not particularly difficult by any stretch of the imagination, but what we're going to learn in our next lecture, which I guess will be a week from today, is called Thevenin's theorem, and it is an alternative way to do exactly what we're doing today that's applicable in all situations. So I'm saying all of this to say it's not going to be a huge thing if it doesn't make a whole lot of sense, because we're going to learn a way to do it better very shortly. All right. So let's talk about practical sources first. So let's say that I have an ideal voltage source like so, and that it is meant to supply 5 volts, okay? So what I want to ask you guys is, what is the maximum amount of current that an ideal voltage source could supply? Would anybody care to venture a guess?
Infinity?
You're exactly right. Now, let me ask you a follow-up question. Is it possible to supply an infinite amount of current in a real system?
No.
Absolutely not, because that would mean that we are generating or we would need access to an infinite amount of charge, okay? Similar question. Let's say that we had an ideal current source. Let's say it was supplying 2 amps of current. What is the maximum voltage drop that can occur across, sorry, that one S looks like garbage, an ideal current source? Anybody care to venture a guess on this one?
Infinite.
Also infinity. Also cannot be physically realized, right? To have an infinitely large voltage drop across a circuit element would mean that we are transferring an infinite amount of power, which obviously cannot happen. So if we wanted to develop an accurate model for something like a battery, and I think we can all probably agree that a battery that we go and buy from the grocery store or Amazon or whatever, it is incapable of providing an infinite amount of current, right? the battery has a fixed amount of stored charge, and once that kind of runs out, the battery is dead. So since there's a fixed amount of charge, there has to be a limit on the amount of current that can leave that thing. Otherwise, every battery would be an infinite source of energy, and we know very much that is not true. Okay, so if we wanted to mathematically model a battery or model it using circuit elements, what we might do is represent it by what's commonly called a practical voltage source. Okay, so in a practical voltage source, we have some source voltage Vs connected in series with some source resistance Rs, like so. So this is our practical voltage source model that we might use to model a battery. And the purpose of that resistance Rs is to limit the amount of current that's capable of leaving the battery's terminals. So for a AA battery or something like that, the value of that resistance Rs is probably on the order of an ohm or two. But for a car battery, which is capable of supplying a much, much larger amount of current, it's probably on the order of tens of milliohms, if not smaller. But there is some small internal resistance that ultimately describes the relationship that will give us the maximum amount of current that could flow out of a practical battery, which we usually call the short circuit current. Okay. So just to describe that really quickly, let me put a blue line over here. So if we were to short out these terminals, the current flowing through this short, we would typically label it as ISC, or short circuit current, and this represents the absolute maximum amount of current that a real voltage source could supply. We could do something fairly similar with a current source. So in our current source, we're going to have our current source representation, IS, so we have an ideal current source. And instead of putting a resistor in series with it, we're going to put a resistor in parallel, like so. And the purpose of this resistance is to limit the amount of voltage that can appear across the terminals of the current source when it is in an open circuit condition. So in an open circuit condition, we might see what's called an open circuit voltage, VOC here. And this open circuit voltage represents the maximum voltage that can ever appear across the terminals of our current source. Because if we connected literally anything else across those terminals, it's going to be in parallel with that resistance Rs and will therefore make the voltage smaller than our open circuit case. So let me write that over here. Practical current source model. So understanding how these two circuits behave in order to limit the amount of current for the practical voltage source and limit the amount of voltage for the practical current source, it is fairly straightforward. It literally just takes Ohm's law to kind of figure out what's going on. What is very interesting about these two models, though, is that under very certain conditions, they can be electrically equivalent to each other. Meaning that if we have a practical voltage source in a circuit and we follow some rules, we can convert it into a practical current source or vice versa in order to make circuit analysis easier for us. Okay. So in order to figure out what those rules are, we are going to look at a practical voltage source connected to some arbitrary load resistance and a practical current source connected to some arbitrary load resistance and see how the voltages and currents and powers compare. Okay. So on the left-hand side here, I'm going to have a simple practical voltage source, Vs in series with Rs. And then across the terminals of the practical voltage source, I'm going to put a load resistance, RL. The value of these resistances do not matter at all. I'm going to define the voltage drop across my load resistance as this voltage VL, and the current flowing through my load resistance as this current IL. And over here on the right-hand side, I'm going to do something very similar. Here's my current source IS in parallel with a resistance RS. So I have a practical current source. And then across the terminals of the practical current source, I'm going to introduce an exact same resistance of RL, like so. And the voltage drop across the terminals of my load resistor is my load voltage VL, and the current flowing through my load resistor is IL. So if we wanted to find the voltage VL in our left-hand circuit, I think we could do that pretty easily just using voltage division, right? So using voltage division, we would have a voltage of Vs multiplied by the resistor that we're finding the voltage drop over, which is RL, divided by the series resistance seen by the source, which is just Rs plus RL. If we wanted to find the current IL, we could do this simply using Ohm's law, where we would have Vs divided by Rs plus RL. And lastly, if we wanted to know the power that could be supplied to our load, that would simply be VL times RL, which is going to look like Vs squared RL over Rs plus RL quantity squared. Moving over to our practical current source circuit, we could find the voltage drop across our load by simply applying Ohm's law. So that's going to look like Is times Rs times RL over Rs plus RL, where Rs times RL over Rs plus RL is nothing more than those two resistances in parallel. We could find the current IL using current division. So that's going to look like Is times 1 over RL divided by, actually, let me make this prettier. 1 over RL divided by 1 over Rs plus 1 over RL. And with a little bit of algebra, this actually comes out to be Is times Rs over Rs plus RL. If you don't believe me for this simplification here, simply multiply the denominator by, so the 1 over Rs, multiply it by RL over RL, and the 1 over RL, multiply it by Rs over Rs, and you'll get this within a step or two of algebra. And lastly, our power is going to be simply the product of our voltage and current. So that's going to look like ISRS squared times RL divided by RS plus RL squared. So if RS is the same in the practical voltage source and practical current source circuits, what condition makes these circuits electrically equivalent? Okay. So to refresh you guys' understanding of electrical equivalence, which I believe we talked about for a little bit before we developed the models for adding resistors in series and adding resistors in parallel. In order for these two circuits to be electrically equivalent, the voltage drop across their terminals has to be the same, the current flowing through their terminals has to be the same, and the power delivered to the terminals has to be the same. So effectively, everything we see on the left-hand side has to be exactly equal to everything we see on the right-hand side. Can anybody tell me what condition makes this happen?
If it follows Ohm's law, we should be able to turn a voltage source into a current source.
Right, but what I'm asking is how do we do that? I 100% agree that we can, but I want to know what the rules are. So let's look
Would
at
it
the
just be an equivalent resistance?
VS equals IS times RS?
Exactly right, Austin, thank you. So if we look here at the voltage, we have this RL over RS plus RL, and we have this RL over RS plus RL. So these things will be exactly equal to each other when VS is equal to IS times RS. If we look at our current relationship, we have a common denominator of RS plus RL. So the numerators will be the same when VS is equal to IS times RS. And here we have this term in common. And once again, we require that VS squared is equal to IS times RS squared in order for these two circuits to be electrically equivalent. So this common factor right here of VS is equal to IS times RS, and I'll be damned if it isn't literally just Ohm's law, allows us to swap back and forth between a practical voltage source and a practical current source. Now, there are some rules here, okay? So if we look at the drawings that I have above, they kind of tell us what's going on. If the positive polarity terminal of the voltage source is on top, then the head of the arrow for the current source should be on top. Transversely, if our current was, let's say, had a direction to the right, then the positive polarity terminal of the voltage source should be to the right. If the current is direction down, the positive polarity terminal of the voltage source should be on bottom, and so on and so forth. So let's take a look at this first in-class assignment problem and see if we can determine the equivalent practical source for each of these practical voltage source and current source things here, okay? So for this guy right here, we have a 10-volt source in series with a 5 kilo ohm resistor. So we know for sure that we are going to have a current source in parallel with a 5 kilo ohm resistor, because the resistor value literally never changes. Because the positive polarity terminal is on top, our arrow should be pointed up. What should the value of my current source be?
Two.
2.
2 watts. Units are important to me.
Milliamps.
Exactly right. So 10 volts divided by 5 kiloohms is going to give us 2 milliamps. Great job. So now let's look at this guy over here. So we have a practical current source because we have an ideal current source in parallel with a resistance. So we know that this is going to be a voltage source in series with a resistance. The 8 ohm resistance does not change. Because my arrow is pointed down, the positive polarity terminal should be on bottom. And what should the value of the voltage source be?
16 volts.
16 volt.
16 volts. Thank you very much. All right. So I'm not going to set this one up. I want you guys to just tell me what it should be, and then I'll draw what you tell me.
Current source in parallel with a 6 ohm resistor, arrow pointing down.
Okay. What's the value of the current source?
Half an amp.
Exactly right. And somebody else tell me what's going on over here on the right.
Do a voltage source in series with the 2 ohm with the positive on top.
All right, so voltage source in series with a 2 ohm resistor.
And
And-
it'll be 14 volts.
14 volts. Great. So this is not remotely a difficult concept to go through. So we're going to work the first part of our next in-class assignment problem by using these source transformation techniques to make a circuit that's kind of a little gross and condense it down into something smaller and more manageable. So we have this circuit right here, and I'm going to tell you guys explicitly, because we haven't learned the maximum power transfer theorem yet, we'll get to that in a moment, that our ultimate goal here is for us to either have a practical voltage source in series with our resistance RL, or a practical current source. In parallel with our resistance RL. And we are just going to use source transformations and then resistor combination techniques in order to make this large, ugly looking circuit look like one of these two options, okay? So that's our ultimate goal. So the first question that I want to ask you guys is, does this circuit that I have below here have any practical voltage sources or practical current sources?
Current source.
So there is a practical current source. The 27 microamps in parallel with the 750 kiloohms is definitely a practical current source. Any other practical sources?
The 15 volts in parallel with the 1.2 mega ohms. Yeah, voltage
It's
source.
in series, but you're absolutely right, Baylor. The 15 volts in series with 1.2 mega ohms is very much a practical voltage source. So let's perform a source transformation on the practical current source on the left. So effectively, how I like to think about this, I'm going to draw a set of terminals here in red. Okay. So I'm going to draw everything to the right of those red terminals. So that would be 3.5 mega ohms. Here we have 1.2 mega ohms, 15 volts. 7 mega ohms. And over here is my resistance RL. And then everything to the left of those red terminals, I'm just going to replace with the electrically equivalent opposite practical source. Okay. So to me, this seems like I should have a practical voltage source like so. This is going to be a 750 kilo ohm resistor. And then I'm going to be real lazy here. And I'm just going to put this as 27 microamps times 750 kilo ohms. I can get a number for that. I feel like it's somewhere in the ballpark, like 21 volts and some change, but I'm going to leave it like that for now. So all I did effectively was disconnected my practical current source, transformed it into a practical voltage source, and then reconnected it across the exact same terminals that it was connected to earlier. That's kind of the key here, okay? So by performing that source transformation, what changed? Or what could we do now that we couldn't do a moment ago?
KVL.
So we can always do KVL. How are the 750 kilo ohm resistor and the 3.5 mega ohm resistor connected now?
They're now in series.
They're now in series. So performing that source transformation allowed us to effectively move that resistor. And so now we can combine those two resistors, making the circuit more simple, right? So 750 kilo ohms in series with 3.5 mega ohms, to me, looks like 4.25 mega ohms. Everybody okay with that?
Yes, sir.
So now I have a practical voltage source on to the left of the red terminals. And I'm going to go ahead and I'm going to put some green terminals right here. I have a practical voltage source between these terminals. And so what I'm going to do is I'm going to perform a source transformation on both of these practical sources. Okay. So let me just draw some things out here. So here's my red set of terminals. This is where my green set of terminals are going to go in a moment. Here's my 7 mega ohms of resistance. Here's my resistor RL. And then here are my green terminals. Okay. So when I convert that leftmost practical voltage source into a practical current source, what I'm going to wind up having is a 4.25 mega ohm resistance here. And then way over here on the left, I'm going to have a current source whose value, again, doing this the lazy way, 27 microamps times, 750 kiloohms divided by 4.25 mega ohms. Is everybody okay with where those numbers came from? So for anybody who's not following, I literally just took this voltage and divided it by this resistance because my source transformation rule is literally just Ohm's law. I'm going to do something similar for this other practical voltage source. So between my set of green terminals, I'm supposed to have a 1.2 mega ohm resistance. Let me draw that a little better. And then over here, I'm going to have a current source that is simply 15 volts divided by 1.2 mega ohms. So what could I do now? Or another way to put this, I guess, if I were to identify my nodes, what would I see here?
Your your 4.25 mega ohm, your 7 mega ohm, and your RL are all in parallel. You can combine
Exactly
them.
right. So if all of those resistors are in parallel, what can I do?
Combine them.
Okay, so I 100% agree with that, but let's look at something else. Let me finish identifying these nodes here, but Baylor is 100% correct that literally just everything is in parallel now. My current sources are in parallel as well, right? Because they're both between the blue node and the pink node. And what happens when I have current sources that are in parallel? I can combine them into a single equivalent current source, right? So realistically, my next step could be to just redraw this circuit as a single current source in parallel with a single resistance in parallel with my resistance RL. So I got this circuit down to something much, much more manageable within just a few source transformations. Now, the thing that I don't like about this particular lecture is that there are so many rules, meaning that we have to explicitly have a practical voltage source in order to convert it into a practical current source and vice versa. When we learn the technique of Thevenin and Norton equivalent circuits next week, we are going to develop a process for effectively doing this source transformation to literally anything, which is why I like it, because it's so much more powerful. But for now, this is what we got. So I'm going to do exactly as Baylor suggested, and I'm just going to say, so 1 over 4.25 plus 1 over 1.2 plus 1 over 7, all of that to the -1 power. So that's just me combining all of those resistors in parallel. And it looks to me like it's going to be 0.825 and some change mega ohms, or 825.436 kiloohms. My value of my current source is just going to be 27 microamps. So that's 27 times 10 to the -6 times 750 times 10 to the 3 divided by 4.25 times 10 to the 6 plus 15 over 1.2 times 10 to the 6. And I wind up getting 17.265 microamperes. So this is what our simplified version of the circuit is going to look like. So now that we have this practical source representation, let's press pause on this particular problem. I just wanted to show you guys how to apply the technique of source transformation. And let's take a look at the maximum power transfer theorem. All right, so let's say that we have a practical voltage source connected to some load resistance RL. Like so. So here's VL, here's IL. And a few moments ago, actually it was more like 10 to 15 minutes ago at this point, we found that the power that was delivered to this load resistance was equal to the source voltage squared times RL over quantity RS plus RL squared. Let me just double check things here. Yep, that's literally just this relationship right here. So if VS and RS are a constant value, we could actually plot the power delivered to our load resistance as a function of our load resistance, and it would look something like this. So here's PL measured in watts, and this axis is going to be RL measured in ohms. So the left-hand side of this graph effectively corresponds to our resistance, or our load resistance in particular, being a short circuit. And as we get closer to the right-hand side of the plot, and I'm just going to arbitrarily put a point here that I'm going to call infinity, this is what our power is going to look like when our load resistance is an open circuit. So hopefully it stands to reason that the amount of power absorbed by our load resistance will be exactly equal to 0 when our load is a short circuit, because there's no voltage drop across it. And so since there's no voltage drop across it, there can't be any power absorbed by it. Similarly, over here at RL is equal to infinity, that means there's no current flowing through our load resistance. And so therefore, there's no power being absorbed by the resistance either. So no current means no power, no voltage means no power. And then everywhere between these 2 points represents literally every possible value that the resistor could ever have. Okay. So if I were to plot this function for PL as a function of RL, it would look something like this. It's not going to be quite so parabolic in shape. It would be stretched more to one side, but you guys effectively should get the gist. So what I'm trying to illustrate here is a couple of things, okay? So the first thing that I want to say is that there is exactly one value of load resistance that corresponds with the maximum amount of power that this practical source could deliver to a load, okay? And we are going to figure out exactly what that is here in a moment, okay? So RL is equal to what is our goal here? But another thing that we can see from the graph is that there are two resistance values associated with every other power that we could want. So let's say, just for the sake of argument, that this guy right here corresponds to 10 watts. If we wanted to know what value of resistance would cause us to absorb 7.5 watts, which would be somewhere in the ballpark of here, it would be whatever resistor is associated with this point and whatever resistance is associated with this point. So one below the maximum power point and one above the maximum power point. So if we're not delivering maximum power, then there's always going to be exactly two resistances that will get us the power that we're looking for. Okay, so let's figure out what this maximum power or the resistance that causes maximum power to occur is going to be. How do you guys think we might do that? So we have a function and we want to figure out where this function is at its maximum. How do we accomplish that?
You have to find the critical numbers.
Find the critical numbers. I think that's probably the same thing that I'm talking about, but could you explain that process to me a little bit? Because it's been a hot minute since I took a calculus class here at Tech.
You would take the derivative and then set the derivative equals to 0.
Exactly right. So that is exactly what we're going to do. Okay. So we're going to take the derivative of our power function with respect to our load resistance. Okay. Now, to me, this looks like we should use the quotient rule because I have a function of RL in the numerator and a function of RL in the denominator. So it's been a hot minute, so please correct me if I'm making a mistake here. But I believe the power rule effectively tells us, so let's see. The derivative with respect to x of, f of x over g of x should be g of x f prime of x minus f of x g prime of x over g of x squared. Does that look about right?
Looks great.
All righty. So,
Yeah.
sorry, what was that?
So that would be it.
Okay, good deal. My memory is less shit than I thought it was. All right, so our derivative is simple, or excuse me, not our derivative. Our denominator is RS plus RL squared. So I'm just going to put that in. And then the derivative of my numerator is just going to be VS, or with respect to RL, is just going to be VS squared. Then I subtract, and so I'm just going to have my numerator by itself. So that's Vs squared RL. And then I need to take the derivative of my denominator, which I believe is going to be twice RS plus RL from the chain rule. And then I put all of this over RS plus RL squared. And I'm going to set this thing equal to 0 in order to find the value of RL that gives me either a minimum point or a maximum point, and there's not a minimum point for this thing. All right, so in order for this ratio to come out to be 0, I really just need the numerator to be 0 because it's impossible for the denominator to be 0 or anything like that that we need to worry about, right? So I'm going to FOIL some things out here. So I'm going to have, let's see, I'm going to have a Vs squared times an Rs squared plus a Vs squared times a twice Rs RL plus a Vs squared times an RL squared. So that's me just messing with this part right here under that red bar. Then I'm going to have minus Vs squared times 2 times Rs RL. And then I'm going to have minus Vs squared, hold on, times 2 times RL squared, I believe. Let me just double check here. So I should have a common factor of twice Vs squared times RL. So twice Vs squared times RL times an RS, twice Vs squared times RL times RL. Okay, so that seems legit. Set this equal to 0. And hopefully we can all see that this Vs squared twice Rs RL minus Vs squared twice Rs RL exactly cancel each other out. We're going to have Vs squared RL squared minus twice Vs squared RL squared. So if I cancel this guy out right here, that allows me to just flip this sign crap to negative, and I'm good to go. So if I move things around, what I have is Vs squared Rs squared is equal to Vs squared RL squared. And it stands to reason then that maximum power transfer occurs whenever Rs is exactly equal to RL. So if our load resistance is identical to the internal source resistance of our practical source, then the maximum amount of power will be transferred to our load resistance. So let me write that out really quickly. So for maximum power transfer to occur, the load resistance RL must be equal to the source resistance RS. So under that, let me see what's going on in chat here. RS plus RL to the fourth power. Yes, thank you. Sorry for not noticing in chat. This definitely should be RS plus RL to the fourth power. However, it doesn't make any difference whatsoever on what we did. But thank you for that. You're absolutely correct. And sorry, I didn't notice that I missed some stuff in chat. My apologies. All right. So if we look at our power relationship, then so PL is going to be equal to VS squared times RL over RS plus RL when RL is equal to RS. This becomes VS squared times RS over, sorry, I missed a squared there, 2RS squared, or 1/4 VS squared over RS. So this is the equation for the maximum power that can be delivered by a practical voltage source. Now, instead of re-deriving all of this, I feel pretty strongly that we can use our relationship for electrical equivalence between practical voltage sources and practical current sources to figure out what the maximum power equation is going to look like when we have a practical current source, right? So for a practical current source, this is going to be 1/4. VS is going to be replaced by IS RS. And so my IS is going to be squared. And so this is going to look like simply 1/4 IS squared times RS. So let me box these equations because these are the things that I really expect you to get out of this. So this is our equation for maximum power transferred by a practical voltage source. This is our equation for the maximum power transferred by a current source. And in order to use these, we need to make sure that our load resistance is equal to our source resistance. So if we go back over to our in-class assignment and we look what we're asked, we're trying to calculate the maximum amount of power that can be delivered to a well-chosen load resistor RL. So if we look at the circuit here, what value of RL will make maximum power transfer occur?
825.436 kilo ohms.
Exactly right, 825.436 kilo ohms. And then how would we find our maximum power? Well, I just gave you guys an equation. It's going to be 1/4 times 17.265 microamps squared times 825.436 kilo ohms. which I get to be 61.509 microwatts. I think I'm off with just a little bit of rounding error because I'm 2 nanowatts off. So I feel like that's pretty darn good.
I did the 10 to the minus 6 and 10 to the third and got 61512. So
Yeah, like I said, we're so close. I'm sure either I have some rounding error here, or more likely I have rounding error from when I did it the first time. But either way, we got the correct answer. So, all right. So that is the last topic for your upcoming exam. So we wrapped up in an hour today, which means we have an hour left for me to answer any questions that you guys may have. And then on Wednesday, we will also have a review session where I will be happy to answer any more questions that you may have. So who has a question?
Where can I find the dates for the test times? Because I was looking on the Canvas and I could not find it today.
So I'm still working on getting all of that kind of stuff set up today. Setting up the exam on Canvas is very, very different than setting them up on Moodle. I did not expect them to be so different, so I'm a little bit behind. So I will just tell you what's going to go on. Let me just put it over here. Okay. So there's going to be a Wednesday option from 6. Actually, I don't need to put 600 and all that kind of stuff. 6 to 9. There's going to be a Thursday option from 2 to 5 and 6 to 9. And then there's going to be a Friday option from 2 to 5 and 6 to 9. So any of those times, just whichever one works with your schedule and or your level of preparedness, take whichever one feels right to you. And there you go.
Thank you.
No problem. And there should be it should be under the exam 1 section. I think it says something like Canvas practice test or something like that. And it requires Respondus and a webcam. And I think it literally says that in the title. If you try to take that thing, I believe it will force you to download Respondus, which means, you won't have to do that right when you're trying to take the test. I don't remember whether I set up unlimited attempts on that thing or not, but I might go back and make sure that's a thing just so that you guys can play around with it as much as you want. Right now, it's only got 3 questions on there. I've been playing with some of the settings. So on Moodle, I'm just going to complain about stuff for a moment here. On Moodle, if I had a question that had multiple correct answers, and I'm sure you've seen some of those on the practice exams, I could set things up such that if let's say a question had 3 correct answers, I could set it up to where if you only picked one of the 3, you got 1/3 of the credit. If you picked 2 of the 3, you got 2/3 of the credit. And if you get all 3 of them, you got full credit. For whatever reason, on Canvas, that is not a thing. It says it is a thing, but I tested it out and it does not do anything. If you don't get all of the answers correct, you don't get any of the credit. So I have specifically put a warning on a problem, and I'm doing something similar for you guys' test, telling you, hey, if you want to get full credit for this question, make sure that you select all of the correct answers. So I'm trying to be as obvious as possible. I did figure out how to do partial credit when there is only 1 correct answer, which is weird that they have that set up. So for example, if I ask you guys a problem that involves determining the amount of absorbed power in a circuit. There will be, the correct answer, and then there will also be the exact same numerical answer with the opposite sign. I am going to give some amount of partial credit if you effectively get the magnitude right and the sign wrong. So you're not gonna lose almost half a letter grade because you missed a negative sign. I want to make sure that that's not a thing. That's something that I've started doing fairly recently, and it seems to help you guys' grades quite significantly.
Do we need to somehow sign up for a certain test time, or do we just get on Canvas and take it?
Just get on Canvas and take the one that suits you the best. You don't need to sign up or anything like that. And I know that this is not a question that you asked. I think I mentioned it earlier or last week, but I want to reiterate it. You're only allowed to take the test once. So you can't take it on Wednesday, do poorly, and decide that you want to take it on Friday after you've had a couple of days to practice. That is cheating, and you will receive a 0 on both attempts. So you only get one crack at this. I know you didn't ask that. I'm not saying it in reference to you. I just want to be very, very clear because I've had that be an issue before.
Gotcha. Wasn't planning on it.
Is there anything that we need to print out before the exam that we're supposed to have in front of us, like paper or?
No. So you should definitely have some blank paper because you are going to be expected to, draw the circuits and all of that kind of good stuff. And also, I want you to scan your work and submit it after you turn in your test digitally or whatever. So like after you submit your answers, scan your work and send it to me just in case I need to look at some things for partial credit and all that kind of jazz. But you're not allowed an equation sheet for this one or anything like that. So realistically, you should just have blank paper, a writing utensil of your choice, and definitely a calculator. Some markers and all of that kind of stuff to identify nodes would probably, or colored pencils would probably also be helpful.
Thank you.
No problem. Any other questions?
Would you mind working out a problem from one of the practice exams?
Not at all. Riley, which one would you like me to work?
The fall 2019 exam. It's question 18 and 19. It has to do with current division, and I just want to make sure I have it all down before.
Absolutely. So let me, I don't have the exams downloaded on this computer, so I'm going to have to pull them up on my desktop and just kind of draw the circuit out. So give me just a moment. And from helping me with FYE, my memory is terrible, and I have already forgotten which questions you asked about.
The fall 2019.
All 2019.
And then it's question 18 through 19. It's like a double question.
Sure. Oh, just one thing that I want to make you guys aware of. So like as Riley just called it, a double question. So one circuit that is pertaining to multiple questions, that is definitely going to happen on this online exam. However, I have it set up because I can't figure out a way to do it otherwise, to where like you're only going to get one problem per page. So you'll just see the same circuit for multiple problems in a row, if that makes any sense. 18 or 19. Okay. So this, let me see what's going on in the chat. Question 7 on fall 2020. All right, let me do Riley's question first, and then I'll do yours, Caleb. Okay, so we have current source like so. So this is 6 amps. Then I have a 4 ohm resistor. This guy is a 2 ohm resistor. Let's see. A 9 ohm resistor and a 7 ohm resistor. And for number 18, I'm trying to figure out this current IX. So let me just put 18 IX is equal to question mark. And problem 19, I want the resistor R3, which would be the power absorbed by the 9 ohm resistor. So as Riley suggested, we're going to approach this using current division. So IX would be, so let's see, we want the current that's flowing through the branch that contains the 4 ohm resistor in series with the parallel combination of 2 and 9. So our ratio part would look like this. And I'd be willing to bet I understand why you have an issue with this, and I'll talk about it in just a moment. And then our known current is 6 amps. And we're looking at the current splitting in the opposite direction that we would expect. So I should put a negative sign here. So this is how I would set things up now, where I'm just using that notation 2 in parallel with 9, as opposed to writing out 2 times 9 over 2 plus 9, which I guess would have just been 18 over 11. That's not that big of a pain in the butt to write. But anyway, on my solution, if I'm remembering correctly, it probably looks something like this.
Yes, sir. That's exactly what it looked like.
Yep. So this trick right here only works when there are exactly 2 parallel paths. And this is the actual thing that I mentioned earlier in today's lecture. So let me just do some algebra for you guys because I'm sure you'll love it. So if I have 1 over, let's say, R1 divided by 1 over R1 plus 1 over R2, I'm going to multiply this guy by R2 over R2, multiply this guy by R1 over R1, and what I'm going to have is 1 over R1. Then I'm going to have R1 plus R2 divided by R1 times R2, and this is the same thing as, let me do it down here, 1 over R1 times R1 times R2 over R1 plus R2. The R1s cancel out, and I wind up getting R2 over R1 plus R2. And all of this ratio would be multiplied by the known current. So when I have exactly 2 resistors in parallel, what I can do is just put the resistance of the path I don't want divided by the sum of all of the parallel paths. The reason why I really, really do not like this method, and I no longer teach it, even though this is what's shown in practically every textbook, is because it's only applicable to exactly 2 resistors in parallel, and it puts the path that we don't want in the numerator, which I and most students find very confusing. So I really need to go back through and update my solutions and all that kind of stuff, because I no longer teach that method, but they will give you the exact same answer. This will is a better way to do it because it's applicable to an infinite number of resistances. So this is the way that I would prefer. And I apologize for not updating my solutions in 5 years and leaving old things that I used to do that I no longer teach. But anyway. So for number 19, we would just do current division again, right? So if I call this current I9, we could say that I9 is simply IX times 1/9 plus 1/2 plus 1/9. And then the power absorbed by the 9 ohm resistor is just going to be I9 squared times 9 ohms.
That makes sense. Thank you.
No problem. Sorry for having shitty solutions.
That's okay.
All right, Caleb, let me go back to the chat and see what you were asking about. Fall 2020, question 7. Give me just a moment to pull that up, please, sir. All right. So in this particular problem, we're given a graph. So let me make a poor attempt at drawing said graph. So let's see. This is energy as a function of time measured in kilojoules. This axis is time measured in milliseconds. And then we have something like this. And then there's some other stuff over here to the right that doesn't particularly matter because the time that we're interested in is 3.189 milliseconds. Okay. All right. So, and let me put some times down here. So this corresponds to 1 millisecond. This corresponds to 3, 4, 5, etc. Okay, so we are asked for the power absorbed by the circuit element at t is equal to 3.189 milliseconds. So P at 3.189 milliseconds is equal to what? So if we were given energy, we need to know how power is related to energy. And I believe, I'm 99% sure, that power is simply the derivative of energy with respect to time. So for us, when we have a graph like this, the derivative of our energy on the interval that we're looking for, which is between 3 and 4 seconds, is literally just going to be the slope of that line segment. So sorry, let me put things here. So we have a change. So we're going to have 0 minus 10, and that's in kilojoules. Over 4 minus 3, and that is in milliseconds, looks like negative 10 over 1. A kilojoule per millisecond is going to be a megawatt. And there we go. No problem. All right, what else do we want to look at today?
I have a quick question.
Sure.
So when we're forming super meshes, how how important is it if one is dependent versus independent?
It is not important at all. The same exact rules apply.
So even if it's a dependent current source, we'll still have a super mesh with them.
That is correct. And even if you're doing nodal analysis and you have, so if it is, let me backpedal here slightly. Any type of current source that is on the interior of a circuit will result in a super mesh. Any type of voltage source, regardless of whether it's an independent source or a dependent source, will result in a super node. So does not make a difference at all whether the source is independent or dependent in either case.
Okay, gotcha.
Homework 6 problem. Okay, actually, let's see. Caleb said number 14, fall 2020. So I'll do that one and then I'll answer your question, Austin. So 14, fall 2020. Okay, so for this particular problem, we are asked to determine the contribution of the 4-volt source to the quantity Vx. So that means very specifically that we are doing superposition. We want the 4-volt source on in particular. So let me draw the original circuit. Give me just a moment here. So here's our 4-volt source. Here is a 7-ohm resistor, 6-amp source in parallel with a 1-ohm resistor. Here's a 3-ohm resistor, 2-volt source, and then over here we have a dependent source that is 0.4 IX. This is our current IX, and this is the quantity Vx. We want to know contribution of 4-volt source to quantity Vx. All right. So since we're finding a contribution of an individual source, that means we are definitely applying the principle of superposition here. So I'm going to leave my 4-volt source on and I'm going to turn off my other 2 sources. So my redrawn circuit with the 4-volt source on and the other 2 off is going to look something like this. And let me think about how I would solve this thing. Part of me is saying, and I don't know that this is going to get me anywhere, but I see that I have Ix prime flowing in and 0.4 Ix prime flowing in to this node, so that this current right here must be 1.4 Ix prime, but I don't know that that actually helps me at all here. So instead, what I am going to do, all right, so this 7 ohm resistor and this 1 ohm resistor are in series, so I can lump them together. So I'm going to replace that with an 8 ohm resistor. And then I'm going to write a KCL equation at this node. So that's going to look like effectively what I'm doing here. It's almost like nodal analysis, but with just one node. So if I choose this bottom node as my ground, what I could have would be Vx prime minus 4 volts over 8 ohms plus Vx prime over 3 ohms minus 0.4 Ix, where Ix is 4 volts minus Vx prime over 8 ohms. Set that equal to 0, and then I would just use the numerical solver on my calculator to solve for Vx prime, since it's a one equation, one unknown system. That's, I think, how I would solve it. Was that sufficient, Caleb, or do I need to go into more detail? All right. So homework 6, problem 2. So let me pull up homework assignments on my other computer real quick. Web work. All right. Let me scroll down here. I'm going to draw this slightly differently just because I don't like those diagonally oriented resistances. So here's a 30 ohm resistor. Here's a 50 ohm resistor. Here's my current source that is labeled as I2. I'm just going to leave it like that. I'll set things up. Here's a 15 ohm resistor. I don't like batteries, so I'm just replacing this with a generic DC voltage source. All right. So let me just think about things here really quickly. So if I were to identify, like I can see very easily that I have 4 meshes. I just want to see how many nodes I have really quickly. So 1, 2, 3, 4, 5. Okay, so I know that this problem is technically from the nodal analysis homework set. I just wanted to see which is going to give us the quicker result. So there are 5 nodes because one of them is going to be ground. It's effectively a 4 equation for unknown system if we do nodal, and it's a 4 equation for unknown system if we do mesh. So because we're looking for a voltage in particular, I am going to choose to do nodal analysis because nodal analysis gives me voltages without any extra steps. I personally would choose my reference node right here. So let's call this node A, B, C, and D, like so. My controlling variable, I'll do it in just a moment, Caleb. My controlling variable Vx is going to be negative Vd. My voltage relationship equation is that the voltage at node C is going to be equal to whatever the V1 is that I was given. And now I can just do KCL at A, B, and D and call it a day. So at A, I'm going to have VA minus VB over 30 ohms plus I2 plus VA minus VC over 15 ohms is equal to 0. At node B, I'm going to have VB minus VA over 30 ohms plus VB over 50 ohms minus I1 is equal to 0. And then lastly, at node D, I would have I1 plus VD over 10 plus VD minus VC over 40 is equal to 0. And then I would solve that system for Vx. Austin, is that sufficient setting things up and all that kind of jazz?
Yes, sir, that makes sense. Quick question. So I've been working at how you're working it here, but for example, when you do the VD over 10, it's VD minus the other node, but you add VD over 10, even though you're going through the negative polarity terminal of VX.
Yes. So when I'm doing my KCL equations, I am ignoring this entirely because it literally doesn't mean anything. So when I'm doing KCL at node D, I'm adding this current plus this current plus this current together. Literally nothing else matters. And I'm expressing everything in terms of VD. Well, Vx isn't a nodal voltage. So that's why it's not showing up in my equation.
Makes sense.
Any other question before I move on to Caleb's question?
No, sir, I see where I went wrong.
All righty, so let's see. Caleb, you were asking about homework 7, number 2. All right. If I'm not mistaken, you emailed me about this one. I'm happy to help. So let me draw this guy real quick. This is the IX that we're looking for. All right, so this homework set is related to mesh specifically, and it tells us to use mesh analysis to find IX. So I'm going to do mesh the first time, and then I'm probably going to solve it using nodal, just because I think nodal is going to wind up being significantly easier. Oh, absolutely. I'll leave all this stuff in the YouTube, Austin. So let's work on mesh first, right? So I'm going to call this guy up top my mesh current IA, B, C, D, and E. There are no current sources. There are no dependent sources, so I can literally just jump straight ahead to my writing my KVL equations. So starting with mesh A, I'm going to have 25 ohms times IA plus 40 ohms times IA minus IC minus V1 is equal to 0. Around mesh B, that's going to look like V1 plus 60 ohms times IB minus ID. Around mesh C, I'm going to have 40 ohms IC minus IA plus V2. Around mesh D, I'm going to have 30 ohms ID plus 60 ohms ID minus IB plus V3 is equal to 0. And then lastly, around mesh E, I'm going to have minus V3 minus V2 plus 120 ohms IE. And I would solve that system of 5 equations, 5 unknowns. Okay. I don't want to erase that per se, so let me show you, just for the sake of argument, how I would do it with mesh, because I genuinely do think it's going to be easier. Not sure. So that's one node. That's one node. That's one node. And that's one node. So right from the jump, we can see that if we do nodal analysis, there are significantly less nodes than there are meshes. So nodal analysis is actually going to be a pretty helpful thing here. And then coupled with the fact that there are so many voltage sources all touching the same node, that's what made me jump like, hey, I should do nodal analysis. So I'm going to put my ground node here. Let's call this one A, B, and C, like so. So what's kind of bananas here, let me make sure that I drew this right, because it actually looks like I'm not even going to have to write a single KCL equation. Yeah, I drew it right. All right. So I can say that my nodal voltage at node A is just whatever V1 is. My nodal voltage at node B is just whatever V2 is. And my nodal voltage at node C is just negative V3. Now, another thing that I can do, so this is also my current IX, which will simply be the sum of this current and this current. So IX would then just be VC minus VA over 30 ohms plus VC minus VB over 120 ohms, and I'm done. So yeah, nodal analysis was way, way easier to do, to use to solve this problem than mesh was. No problem. Any other questions I can help you all with? Scroll up a bit. Absolutely, Brian. Tell me when to stop. Or is this where you want it? Yep, okay. Caleb, that's correct. Wednesday's class meeting is dedicated entirely to being a review session. So I will be available, as far as I know, for the full 2 hours just to answer any questions you may have. All right, I'm going to mute myself here for a moment. I'll hang out on Zoom if anybody pops up with another question. I'll just be working on your test on my other computer. So, like I said, if you got a question to ask me, let me know.
Dr. Hartman, I have two questions really quick. Just like general questions, not workout.
What's up, Raleigh?
So on one of the exams or the practice exams, it like tells you what to use, like when you want to see nodal or mesh. Are you gonna follow that? Because on the another one, it just kind of says like find whatever you're looking for, and you get to choose whether you're using nodal or mesh.
I am genuinely surprised that I ever wrote a test that told people which analysis method to use. I have no intention of doing that. So
Okay.
it will be up to you to determine which circuit analysis technique to use. That
Okay.
being said, typically speaking, the exam follows the order that we went over material in class.
Okay, awesome.
Yeah.
And then on Wednesday, I know I have work all day. So is there any chance that you will record the review session and post it either like Wednesday evening or Thursday morning?
I will absolutely record it. I am trying. I just want to apologize to you guys for being a little bit tardy with getting the videos up. I got so used to having one of my student workers do it that I forget that I have to do it for this class because it's the first time in a year that I've had to do it. So I will absolutely endeavor to get that video up by Thursday morning for sure.
Awesome.
Yeah, I have every intention of recording it. And if you don't see it up by, let's say, 8 o'clock in the morning, shoot me a text and call me an asshole, and I'll get it up there.
All right. Thank you so much, Dr. Hartman.
No problem, Riley.